the whole noise supply. So today we'll talk about experiment 5 and experiment 5 called VSEPR, VSEPR. So, and let's put what is V stand for. This is valence, correct? S, shell. P is electron. P is pair. And R is repulsion, correct? So, those are the abbreviation at the time. It's really about molecular shape, molecular shape of the molecule. So molecular shape of molecule, correct? So, and with this here, we'll have the opportunity today to make some shapes. Okay, using our model here. This is the model here. You can see it as this is the model B using the molecular model. We'll do some shapes, and you'll be asked to make a pictures of your own shape. Correct? So let's first go for a recitation, which is about 30 minutes recitation we need to know what is really VSEPR. VSEPR here. These guys here. VSEPR here is a theoretical model which describes the shape of a molecule, correct? And that's what the whole thing is all about. It describes the shape of a molecule. So what's happening is we know in the molecule is and this is only for the molecule is covalent what? Covalent molecule and not ionic, not ionic molecule, correct? So it's mostly for covalent molecules. And we know that covalent is non-metals combined, no metal there. So that's what the whole thing. How the whole thing is coming in this theoretical approach is. The theoretical approach will tell us that the molecule has a lot of valence electron share, correct? So it is molecules have valence electrons shared, correct? They are sharing. Our valence electrons are negative particles, correct? Negative particles, correct? They are negative particles, they tend to repel each other. All those particles tend to repel each other. To minimize, correct? To minimize this repulsion, correct? The molecule will have to have a shape that minimizes the repulsion. Minimizing the repulsion, correct? So this is the whole idea. I'll give you an example of this. This for here, number one. An example of this, for example, let's look at an example here. Here it is, guys. Number 1 here, this number 2. An example of this I have here, correct? I have here, for example, methane, correct? This methane here, this is called methane. So if you look at this, methane here, and if I look at this, it looks like this. That's the Lewis structure we're talking about, and then the Lewis structure here. So all those here, those are the VEs repelling each other, correct? Are repelling each other. The VEs means the valence electrons are repelling each other. So here it is, go shared. So the repulsion here will be minimized. Repulsion will be minimized when a tetrahedral shape is reached, correct? So the molecule is still fighting this repulsion, because repulsion means instability, correct? So here it is, repulsion. Repulsion means repulsion here means what? Instability. So repulsion means instability. So when the molecule starts, the atoms within the molecule start repelling each other, that means instability. We have to have stability, and this stability here reaches what? The tetrahedron, most stable shape, most stable. So this repulsion here will be taken away, and then will be more stable, correct? So this is just symbol. What is really VSEPR? The VSEPR, what is it all about? Now, before we know the shape here, VSEPR, so the whole idea is what it's doing is predicts the shape which is most stable, correct? Most stable of a molecule, correct? That's the whole thing is about this VSEPR. So what it does, it's really predicting the shape of a molecule in a very most stable form, correct? So then we have, in order to get this, we have Lewis dot structure helps determining the shape of a molecule, correct? So what is Lewis dot structure is all about? What is Lewis dot structure all about? So it is number 2, number 3. Lewis dot structure it is, and remember that's just only for a covalent bonds, correct? Or molecule, not ionic, correct? So in Lewis dot, the VEs, the valence electrons, are represented as dots, correct? Are we following here? And the elements are represented by their symbol. By their symbol. So if I have, for example, methane, an example here, just to show you an example here, methane. So what we'll have here, each carbon here has 4 valence electrons, correct? I can box them just to make emphasis. This is my 4 VEs, correct, of carbon. And here I have hydrogen, here I have another hydrogen, here I have another hydrogen, and here somewhere I have another hydrogen. So I will box all those here, and this will tell me this is the hydrogen with 1 valence electrons is there in the molecule. So now, this is the Lewis dot structure. Is the valence electron is as dot, and then the symbol of the element. Now, in order to have a covalent, you start with the single bond. So one single bond is this called here single bond. We are sharing what? Sharing 2 VEs. One from hydrogen and 1 from carbon. So those are 1 hydrogen, 1 carbon. So this one is single bond. There's another single bond here, guys. Correct? And there's another one here as well. And there's another one as well. So you can see we have 4 single bonds. And you can say those are, each bond is 4, we call them groups, correct? Those are 4 groups. Each single bond is considered as a group. So single bond as well. Double bond as well. Triple bond as lone pair, correct? As lone pair, there by itself, electrons is not connected. Lone pair are considered as one group. So we treat them as such. We treat them as one group, correct? We treat them as one group. So we have here connected all those here. You can see here connected all those together, correct? So now we have 4 single bonds, 4 groups. And this is, when I have this, I look at the table then, I look at the table after. So I have 4 groups, correct? Look at the table here. And then from the table here, I can, this table will tell me that those are, from the table, those are, this is a tetrahedral shape, correct? Tetrahedral shape. So, now, when drawing this structure here, number 4, I will scan it, don't worry, I'll scan it. So here it is. So here, it is when drawing Lewis dot structure for covalent bond, then one has to consider the following, correct? One has to consider the following. Which one? First of all, electronegativity, correct? Negativity. So electronegativity means the most electronegative atom, means what do you mean by electronegativity? Electronegativity is the ability of an atom to pull out adjacent valence electrons from other atoms here within a chemical within a chemical, correct? Within a chemical compound. Everybody following here? Fluorine is the highest. So this is highest electronegative atom, correct? Oxygen, second highest electronegative atom, correct? So you have to consider electronegativity, and you keep, in general, you keep, here it is, in general, the central atom, the central atom will be kept, will be the least electronegative, correct? That's electronegative atom. The terminal, the edge, the terminal atom, which is the edge, will be the most electronegative atom, So we know that the most electronegative will be at the edge, and the central will be the least electronegative. What's really striking about this number one, about the hydrogen. Hydrogen, on the other hand, that's number one, correct? Number two, hydrogen, this one, hydrogen. If you look at hydrogen, hydrogen is always drawn at terminal, at edge. At terminal was at edge, correct? And one single bond. And I said it's always, no exception, always. Number three, we talked about octet rule. Octet rule is, we'll consider mostly is elements such as carbon, nitrogen, oxygen, and fluorine. They have to have 8 electrons, bonding and non-bonding. Have to have 8 electrons surrounding them, and this is bonding or non-bonding. Okay guys, this is the most important now rules. Let's look at those rules, and then let's put some examples so we can see. So those are the octet rules. They have to have 8. If I look at this, except for hydrogen. So other elements, look, other elements might or might not satisfy the octet rule, correct? And if you look at this, let's have carbon dioxide here. Example here, CO2, correct? I have carbon and oxygen are a must, correct? Octet rule is a must. This is a must. Octet rule is a must here. So how we do this? Well, the oxygen is most electronegative. If you look at the table there, electronegativity table in your book, we'll come back later on. That's the chapter 7. If you look at this, you'll say carbon has 4, correct? 1, 2, 3, 4. Oxygen is 1 here, 1, 2, 3, 4, 5, 6. And oxygen here has 6 valence electrons, so 6. And if you look at this, each of those have to have what? Have to have 8. So I'm connecting first to start with with single bond. Start with single bond. If the single bond not satisfy octet rule, do double, then do the form the double bond. So if single bond will not satisfy the octet rule, so then go for double bond. Go for double bond. So now let's put here 1, correct? By doing this, if I count this one here, let's count, guys. For carbon, 1, 2, 1, 2, correct? 3, 4, 5, 6. So no octet rule, correct? And here for this oxygen, 2, 3, 4, 5, 6, 7. That's 9. And here 1, 2, 3, 4, 5, 6, 7. So this 7 VEs, and this is 6 VEs, correct? And this is 7 VEs. But those they have to have carbon atoms. They have to have what? Octet rule. But they have 7 or 6. So single bond will not do it for me. So I have to move this one here and this. Move them here and move this one here to make double bond. So now let's look at this. This is 4, this is 5 here. Let's look at this, guys. So here it is. What I'm doing here, remember I did this one here, correct? And we did this, and this one here, this one here, this one here, this one here. So this one was started with. This is not does not obey the octet rule, and not the correct structure. So what I will do here, I'll put this one here, correct? Up front, I'll put this one here. I'll put this one here. I'll put this one here. So I have now. I have what? I have 2 double bonds here, correct? I have 2 double bonds. I put this one here, the other one, I put this one here, and then let them share. This is 2. Now, if I look at this, 1, 2, 3, 4, 5, 6, 7, 8. Carbon is good. Octet rule is good. 8. 8 VEs. How about oxygen? 1, 2, 3, 4, 5, 6, 7, 8. That's correct. We have 8 here. Surrounding, correct? That should be surrounding. Oh, shared or unshared? Shared or unshared? Here, shared or not shared, right? Now here is the same thing, 1, 2, 3, 4, 5, 6, 7, 8, and this one here is 8, correct? VEs. So then the final structure here will be, here it is. Correct? So this one here has the shape of linear. So this is what linear. Any questions so far? The last topic, and then we'll start doing some examples. The last topic is VSEPR code. VSEPR code. So what is really VSEPR code? VSEPR code will give us the opportunity to look. We'll make a table of this VSEPR code, and we'll say A with symbols, A, those codes here. A is given to central atom. So central atom. B for the terminals at the edge, and E for lone pair. Correct, guys? So if I have CO2, for example, correct, and I have here with the structure of so then I will say central atom is A. I'm trying to get another pen. I hope it's the red one is working for us. I hope so. This is A. This is A. This is B. This is B. correct? A, B, B. Now, we look always consider what? Consider the central atom. And this is central atom, correct? Now, the code of this will be, the code will be AB2. Why is AB2? Because I have one central atom and two terminals. So AB2. AB2 from the table here, from the table, is linear. Correct? You see it here, it's linear. So from the table here, I know this AB2 is linear. Lone pair, there's no lone pair. We'll come back to it. But just this is the code. We can have a table and then look into the whole thing. So now let's go for the examples in our lab today. What are those examples here? Well, they are here. You look at the lab, the beginning of the lab here, and we're looking at this one here. So here's the goal of the experiment expressed for you here. That's the goal, correct? The whole idea is to get our what we call it, our shape for this molecular shape for those molecules. So the first one here called H2S. The first one here called H2S. And if you look at this, you can fill it there, because what I want to do with this, every student here, you will have the picture somewhere. You write me the Lewis structure here, correct? So here it is, the Lewis structure here, and you make a picture snapshot of yours. I'll take 10 points for what? For the pictures. You have to make a picture. And if you don't know how to minimize the picture to fit here, come and see me, I'll show you. Come please see me, I'll show you how to do the picture. So we'll split this square or this column here in two. One is the Lewis structure, one is the picture. So here's the Lewis structure, Lewis dot structure here, and here is the picture or the image, correct? So, and you can blow up this one here in Microsoft Word. You can blow it. No other format. Do not use PDF or pages or Apple pages or links or whatever. Just the format of Microsoft Word, the same file you can. So let's look at this. We'll go step by step, and we'll go through them step by step, correct? The first one called H2S, correct? The first one called H2S. So let's look at this. H2S. So everybody's following me here? We'll do this together. We'll do what? All this together. And then some columns are missing. Some columns are missing, and as we go there, I'll show you what they are missing, and then you can fill them in as a piece of paper, or you can just squeeze the column there. So first here, that's the experiment, correct? So the experiment here, we have the first one here. We have to get H2S, correct? The first thing here, we have to calculate the total VEs, correct? So what is the total VEs? To check up total VEs. This is we're using for checking up the total of VEs, correct? So sulfur, what's group sulfur in? 6. Group 6, correct? How many VEs? 6 VEs, correct? I have sulfur here. I have hydrogen, 2 hydrogens. What's group in? 1. I have 2 of them, correct? That's 2. That's 2 here. Multiply by 1, how many? 2 VEs. So total how many? Total is how many? 8, correct? Total is 8. So now this is number 1. Number 2, I want to look into the Lewis dot structure of this, correct? Now with this here in mind, hydrogen always what? at the edges, no exception, always. So I will have here hydrogen with 1 valence electrons, group number 1, and box it. And then here is another hydrogen, box it. And the sulfur, how many you said? 6. So it have 2, 2, 2, and 2, and 2 here. So, and then I'll start connecting together. I'll start what? Connecting those together, single bond. Are we interested in octet rule? No. You don't have to consider. So, no need to consider.
Professor Isaiah?
Yes. So
That's
consider
sulfur, right?
hold on, octet rule. Yeah, what's your question is?
You said sulfur's in group 6?
Group 6, yeah. Yes, group 6. Underneath the oxygen. Look at the periodic table underneath the oxygen. Group is the column. The periods are the rows, correct? Underneath the oxygen. So, now we have here, guys, look at this. This is we are not looking for octet rule here because there are no carbon, nitrogen, oxygen, fluorine atoms, correct? If we have those, it's a must. Any other ones, we don't have to worry about. Sulfur can violate the octet rule. Any element can violate the octet rule, correct? But not those 4. Those 4 you cannot violate. You have to have them. Must. Correct? So now, let's look at this. I have here is a central atom, correct? A.